right? We are discussing about different types of solar collectors and the classification of the collectors. The classifications are passive and active. Will focus mainly on the active type of collectors. And in active type of collectors, again, you can have main categories like solar photovoltaic type of solar collector and solar thermal collectors. And the other way to categorize them is whether they are fixed or some component is moving, and this motion is done generally to track the sun. So whether they are tracking or non-tracking, again, in tracking you can have single axis tracking or two axis tracking, and then under each category you can have different types of collectors. Then we started talking about the flat plate collectors, and the flat plate collectors are they look like or their absorber plate is flat, so we call it flat plate collector, and they are generally the stationary collectors, and they don't track the sun. They are put at fixed inclination, but they are because of simplicity they are very popular type of collector and more economical type of collector. So unless you need you need a bit higher temperatures, you generally uh, try to look for a flat plate collector option, and in that you have the simple flat plate collector evacuated tube collector, or even CPC is many times a fixed type of collector, though not exactly flat plate collector. And a solar water heater is a very common example of a flat plate collector, and we try to understand different components and functioning of this type of collector with the help of the diagram, the exploded view, two-dimensional sectional view of a flat plate collector. Right now, there is energy conversion taking place in a solar collector from electromagnetic waves to thermal or electrical energy. So whatever is your useful output divided by whatever is the input energy, that ratio is called the efficiency of the collector. And we are concerned about the efficiency of the collector because higher the efficiency of the collector, less the area you need for collecting same amount of energy over a period of time. So one type of loss which will occur before like you convert it or you take it out in the form of useful energy. One type of loss is optical loss. That is, if you talk about the flat plate collector, when the solar rays or radiation pass through the glass, there is some transmission loss because the transmissivity of glass is not 100%, and there is some absorption, there is some loss in the absorber plate also, that is absorptivity is also not 100%. Okay, so what is available to you, let's say transmissivity and absorptivity both are 90%, 0.9, 0.9. So 0.81, 81% is available to you, and 1 minus 0.81, that is 19%, is loss. So this loss is optical loss. The other type of loss is thermal loss. This happens after the radiation has been absorbed in the in the absorber plate. So when the radiation is absorbed in the absorber plate, it achieves a temperature higher than the ambient temperature. So you have created a potential difference, the temperature difference, which will be responsible for heat transfer, or in this case, it is a loss. So there could be heat transfer in different ways. In different ways, the three modes of heat transfer: conduction, convection, and radiation. There are chances for all of these the modes to happen. Okay. So with the help of this diagram, this is a like these numbers that are shown here, percentage are typical or representative numbers. This is the actual numbers could be close to this in case of an actual flat plate collector also, but it's not that it has to be this many percentage for each collector, right? We are talking about the numbers which are generally in this range in a flat plate collector. So out of the total energy that is falling on the glass, and these are the components of the flat plate collector, the absorber plate and the glass, and then there is air which is trapped in between. And then from absorber plate, finally you are taking out heat, which is the useful heat. So out of the total radiation, solar radiation that is falling on the glass, here it is shown that the absorption in glass is 2% of that and reflection is around 8%. Okay. If you use even a better quality glass, low iron glass, you might be able to reduce the reflective reflection, or you can put anti-reflective coating on the glass and you might be able to reduce this percentage. But as of now, let us take this as, let's say, 8% and absorption as 2%. This means that there is some reflection occurring when the rays strike the glass. Though we say that the glass is a transparent material, transmissivity is not 100%. Here it is shown that it is around 90%. So 8% loss by reflection and 2% by absorption. So 10% is lost actually because of the glass. Now remaining portion enters into the collector and it strikes the absorber plate. Now absorber plate should ideally absorb all the radiation which is striking it, but again it can never be an ideal material. As it is shown here, 8% of what is this is 8%. Everything is shown as a percentage of this 100%, right? So 8% of the total, around 8% of the total is, let's say, reflected by the absorber. There is nothing like transmission in case of absorber, absorption and reflection. So 8% is reflection loss. Now this is reflection, this is not emission. So reflection is still short wave radiation and it can easily pass through glass and it is lost to the ambient or sky. So this is a reflection loss. So this reflection loss and the loss at the glass, these two are the optical losses. Now remaining, that is, this is 18%. So remaining is 82%. So remaining 82% is absorbed by the absorber plate. When you say it is absorbed, it gets converted into heat. Right now we are talking about solar thermal collectors, not solar photovoltaic, which convert it into electrical energy. We are talking about the conversion to thermal energy or heat energy. So that absorption converts the energy into heat energy or thermal energy. So the absorber temperature increases, absorber plate temperature increases. Now it is at a temperature higher than the ambient temperature. Let's say the temperature is 95 degrees Celsius or let's say 90 degrees Celsius. The ambient is, let's say, 35 degrees Celsius. So obviously there are chances that this heat will try to take the required route and try to leak into the atmosphere. Now what are the different channels or different modes of heat transfer? So one of them, very important one, most of the times a dominant one, is by mode of convection. So what happens is there is air trapped in between, right? But there is enough gap for convection to take place. This is of course natural convection. Okay, this is not forced convection. If you know the difference between forced convection and natural convection, if there is some external device which is driving the flow of the fluid, then it is forced convection. But here it is due to the buoyancy force generated because of the temperature difference. So it's natural convection. So this air which is in contact with the absorber plate heats up. This air heats up, its density decreases, it starts moving up and it comes in contact with the glass. Now the glass on the outside, there is air or there is air flowing over that, right? It's wind, which is, it may or may not, like it may have high or low velocity, but still you can always say there is always some velocity attached to air, and which is called wind. So there is some wind velocity. Because of that, on one side the heat is supplied by this hot air. It has to pass through the glass by mode of conduction, and finally it comes on the outer surface. So if you touch the outer surface, you should feel it hot, because it is, and that temperature is higher than the ambient temperature. So air takes away heat from here, right? So though it's just shown convection here, it is combination of one, natural convection taking place here, two, conduction through the glass, and three, again forced convection taken or taking place here. And finally, that's how the heat is dissipated from the absorber plate to the outside atmosphere by mode of conduction to the air or wind. So this is one type of loss, convection loss, which is shown to be around 13% here. So this loss is also called top loss, because it is occurring from top. Actually, some loss also occur from sides, right? So there is some side loss also, but it is comparatively less as compared to the top loss. Of course, convection is not the only top loss. There is a radiation loss also from the top. Yes. So this is about the convection or convective heat loss occurring from a flat plate collector. So you out of this 100%, you lost around 13% by convective losses. This 8% was already lost by reflection. Now this absorber plate, it is at a temperature higher than the sky temperature and also higher than this glass temperature. So what happens is, like, if glass is not there, then in case of convection, what will happen? You don't have natural convection and conduction. These are actually, in a way, you can say resistances. So those won't be there. The air will come in direct contact with the absorber plate and take away heat. So this 13% would increase to much larger percentage. Okay, so this is one of the reasons why you are putting glass. Then second one is that absorber plate has a particular temperature, ambient is at a particular temperature, or sky is at a particular temperature. Let's say absorber plate is at 90 degrees Celsius. The sky is, let's say, at 30 degrees Celsius. The glass is, let's say, at 45, 50 degrees Celsius temperature, right? So there is radiation or re-radiation or emission. Now this is radiation or emission, and this was reflection, right? So I hope you are able to understand the difference between reflection and emission now, right? Emission is because of the high temperature achieved by this component or surface. So radiation happens whenever there is a temperature difference between two surfaces or bodies. There will always be a net heat exchange between the two bodies if the temperatures are not same. So the absorber plate gives away heat to glass, and glass finally gives it away to the sky if it is open to sky, right? Normally, we don't like take the surrounding structures, tall structures, if any, into account. Otherwise, the analysis will become very difficult. So the glass loses it to sky. So the radiation finally is lost to the sky. Okay, so this is a radiation loss. Now, the third type of loss is shown here, the conduction loss, heat conduction. As you can see, it is shown as 3%. This radiation was shown as 6%. Right? As I told, these are representative numbers, and this is for a flat plate collector, which is operating at temperatures. That is, it is used to heat up a fluid at temperatures around 70 degrees Celsius or so. So let's say this is a water heater, and it delivers water at 70 degrees Celsius. Right? So these numbers might be true for that type of application. The numbers will change if that operating temperature or application changes. Okay. Higher the temperature, generally overall losses increase, as well as the contribution of radiation increases. As you know that radiative losses are proportionate to the temperature raised to 4 and the difference between the two temperatures. So it can increase rapidly beyond certain temperature, right? So radiation loss comparatively low here because it's not a very high temperature application perhaps. So the radiation losses are less. Okay. Now, heat conduction, the loss is shown to be 3%. Now this seems to be comparatively low value. Okay. What is the reason for that? For a lower value? Because there is insulation not shown here, but insulation is put below this. If you recall the components of a flat plate collector, right? There is insulation below this, and that is generally good insulation, very low thermal conductivity or high resistance offered by that, and because of that you are able to reduce the conduction to a conductive loss to a great extent. Okay, so it's only shown as 3%, right? So these are the different losses occurring. So one loss we talked about, optical losses, which is like the transmission loss here and the absorption loss here, right? And then once it is absorbed, there are different ways in which heat loss occurs. Okay. So this is about the heat transfer phenomena in a flat plate solar collectors. Now let us focus on the efficiency of a flat plate collector. What are the factors affecting the efficiency of a flat plate collector? So we'll do some kind of manipulation of the formula for efficiency, and that will help us to identify the parameters which affect the efficiency of a flat plate collector. So once you understand which are the parameters affecting, accordingly you can try and either estimate or you can try and change the parameters so that you get higher efficiency. So efficiency is useful energy upon the input energy. So useful energy is something which is absorbed by the absorber plate, right? That is Q ABS, what is absorbed. So this is after the absorption takes place. So transmission loss and absorption loss is already taken care of, right? Transmission loss and absorption loss are already taken care of here. And then even after that, there is a loss. The three type of heat transfer loss is QL, right? And this is QI, that is in the denominator. Now these losses are take place by three different modes as just talked about. But here there is a single equation written, QL is equal to UL into area of the collector into TP minus TA. This TP is plate temperature, the absorber plate temperature. TP is absorber plate temperature and A is the ambient temperature. So this is the potential for heat transfer. And if you just think about the convective, the Newton's law of cooling, then it's proportionate to the temperature difference and the area and the heat transfer coefficient, right? Now here it's this AC is the area, UL is not just convective heat transfer coefficient, but it is called overall heat transfer or heat loss coefficient, U suffix L, L is for loss. So it's overall heat loss coefficient for collector, and it is actually combination of you are representing all different modes of heat transfer or total heat transfer with a single equation, this equation, right? UL. So UL is an effective heat loss coefficient which combines all different phenomena, convection, radiation, as well as the conduction losses. So you would like to get this value of UL, loss coefficient, for a collector, right? So the collector has to be tested by a standard test, and the manufacturer has to specify what is the loss coefficient. Now, what is the what is the efficiency? But actually, efficiency is not a single number, as it will be shown later. It depends upon different parameters. So it cannot be given as a single number, but it is rather represented as a graph, right? It is something like, even in automobiles, you can't state the mileage, right? That the mileage is this many kilometers per liter. It always varies. Like on highway, it will give some other number, and on in cities, it will give some other number, right? So similar to that, you cannot give a single number for a efficiency of a solar collector. You have to give different information, and only then the efficiency can be stated. So UL is the loss coefficient, which is, in a way, you can say it's a constant, right? For a given collector. So it depends upon the type of collector and the material of the collector, etc. So UL value has to be stated. Now we can rewrite the formula for we want to rewrite in a particular way. One of the reasons why we want to rewrite is we don't want this plate temperature here. And why we don't want plate temperature is, actually, you can say there are two reasons. One, plate temperature cannot be directly measured. Why? Okay. Why it cannot be measured directly? Because it is inside the collector, and it's not that it cannot be measured, but it's normally not very convenient to use to measure it. And again, it's not a single temperature. Over the plate also, the temperature would vary, right? If you again recall the diagram, the plate, the tubes, the water tubes are embedded in the absorber plate. So and it was written as the absorber fin. So what does fin mean? Fin means that there is a temperature change along its length. So near the water tube, the temperature would be lower, while in the middle, between the two tubes, yeah, okay, that will be higher when it is away from the tube. So plate temperature is not a single temperature, and cannot be conveniently measured. So it is to be replaced with some other temperature, and that temperature is generally the fluid entry temperature, TI, which is measured while testing a collector. Okay, so that is one thing. So we would like to replace this TP with TI. Okay, or sometimes the mean temperature of the fluid is also used in some of the standards to replace the TP. Okay, so when you do that, you are introducing one constant or one parameter, which is called heat removal factor, this FR. Now this QU, what is QU? QU is QI minus QL, right? So this QU is QI. QI is the input energy, right? Here, this one. So Q absorbed minus the Q lost. So how much is the heat absorbed? The heat absorbed is S into AC. Now, what is this S? S is what is absorbed by the absorber plate. How much is absorbed by the absorber plate? It is IT into tau into alpha, right? IT is the total radiation which is falling on the collector, let's say 900. Then the glass transmissivity is let's say 90%, and the absorber absorptivity is, let's say, 90%. So 0.9 into 0.9, 0.81 into IT, right? So 0.81 into 900, right? That would give you S. So it is still, it is in watt per meter square. So this is the energy which is absorbed by the absorber plate. this is what is absorbed by the absorber plate, and then some part is lost by different modes of heat transfer. Okay, so this QU, when you change this, when you want to change this temperature, uh, TP with TI, you are putting FR. The definition of FR would emerge later. So this is heat removal factor, and this is energy falling on the absorber plate minus the energy that is lost. Right now, I can take this area of the collector out of the bracket. So this will be just S, and here what is QL? QL is equal to UL into AC into TP minus TA, but this TP is to be replaced with TI because we have already multiplied this with FR. So AC is taken out, and this is UL into TI minus TA. Okay. Now we put this in the formula for the efficiency. So Q absorb minus QL upon QL. So this Q absorb minus QL is given by this portion, that is FR into AC into bracket S minus UL into TI minus TA. And how much is the energy which is falling on the collector QI? It is equal to IT into AC, right? Area of the collector. So if it is, let's say, 900 watt per meter square into area is, let's say, 2. So it is 1800 watt per meter square. That's the input energy. Okay. Now this, what we are doing is, like, this S is nothing but IT into tau into alpha. Okay, so that is shown here. Now this FR is common to all. This AC gets cancelled, right? Because it's there in the numerator as well as the denominator. If your gross area is almost equal to the aperture area, this can be done. So area of the collector, this gets cancelled, and what you have in the bracket is like outside the bracket is it is FR, and in the bracket you have tau alpha minus UL. Okay, what you have done is this IT is also taken out and it is cancelled. So here you have IT in the denominator for the second term. Okay, for the second term. So UL into TI minus TA upon IT. Okay, and there is a particular reason why this is done. If you look at these things, uh, this is actually in the form of this equation of efficiency is in the form of a equation of a line. So first term is FR into tau into alpha. All these are constants, right? So this is C. Y is equal to mx plus C. So this is that constant or intercept. And second term is FR into UL into this thing, Ti minus Ta upon It. Now this Ti minus Ta upon It is considered the variables. You can vary Ti minus Ta, right? Ambient temperature may not be in your total in your control, but at a given ambient temperature, you can change Ti, and accordingly you can change this parameter. And IT, that is amount of irradiance, watt per meter square, the total heat flux falling on the collector can be varied. So this is Y is equal to, you can say, C minus mx, right? So it's an equation of a it's an equation of a line. And what is C or intercept? C or intercept is FR into tau into alpha. And how much is the what is X? X is Ti minus Ta upon It. So when the graph of efficiency is plotted versus Ti minus Ta upon It. Ti minus Ta is also can also be written as delta T. That is the temperature potential for heat loss, and IT, right? So that is put on the horizontal axis, Ti minus Ta upon It, and this efficiency is plotted against that, and the slope would be minus FR into UL. So it's a negative sloping line. Okay, what does it mean? Like when the graph is shown, I'll explain you what does it mean, right? Okay. Okay. Now here
how are you going to draw the graph for efficiency? This is the equation for efficiency. We would like to write the equation in this form, but you beforehand you don't know these parameters, like what is FR for my collector. Unless I test the collector, I won't get it. What is UL for my collector? Unless I test it, I won't get it, right? So after testing, you get these terms and then you show the efficiency or write the equation for efficiency. But that has to be done by testing the collector. So let us see how a solar collector is tested. So this testing has to be done like many other products. The testing has to be done. Again, let's say automobile, they will be tested at a particular at particular conditions, and then certain parameters would be given that at this many RPM it will give this much torque, and at this speed it will give this much mileage or things like that. So similarly here, a collector, and this testing procedures are most of the times standard procedures. You have to follow certain standards. So similarly, for flat plate collectors, or for that matter any type of solar collector, there are standards formulated, and accordingly you have to test the collector. So what is the standard procedure of testing a collector? That will be shown now. But just before that, this is the time to define this heat removal factor, FR. So you know the useful energy. The other way to measure the useful energy is to get MCP delta T. Let's say you're heating water. So what you're doing is you're pumping water. Forget about the domestic water heater where there was natural convection. But if you are, let's say, pumping the water, so the mass flow rate of water and what is the temperature difference created and the CP of water. So that's your final product that you want to get. So that is also useful energy. So this FR, heat removal factor, is defined as the ratio of heat actually delivered by the solar collector, that is MCP into TO minus TI. TO is outlet temperature of the fluid which is pumped into the collector, and TI is the inlet temperature of the fluid which is pumped into the collector, divided by the delivered by the solar collector to that delivered if collector were at uniform temperature equal to that of the entering fluid. And if you keep the whole collector at TI, the inlet temperature, actually collector plate is not at TI, collector plate is at TP, right? Which is, you may say it's not a single number, but still you can have some representative number TP. But here you are not writing TP, but you are writing TI, right? So if the collector whole plate were at TI, then this, what you see in the denominator, would be the heat delivered by the collector. That is useful energy, right? But actual useful energy is MCP TO minus TI. So this FR is ratio of the heat delivered, actual heat delivered by the solar collector, which would be a bit less than the heat that can be delivered if the whole plate were at temperature Ti, the inlet temperature of the fluid. Now this Ti would always be less than Tp, right? Because it is the inlet temperature, then the plate temperature always has to be higher than the inlet temperature, only then there can be heat transfer, right? So the denominator is less, it means that FR will always be less than 1. Okay. Now this figure, which is shown next, gives you the performance, or it explains the procedure for testing a flat plate collector. Why is testing done? Testing is done to plot the efficiency graph. What it is plotted against? Efficiency is plotted against Ti minus Ta upon It, the total heat flux that is falling on the solar collector. Okay. So how is this testing? What is the procedure for testing? You can see this one solar collector shown, and a solar collector is shown. And then what do you see at over that solar collector? what you see over that solar collector is shown as solar meter. Actually, it looks something like a pyranometer. So if you are interested in the global or total radiation falling on the solar collector, you can put a pyranometer. Actually, it is not put on the solar collector. It will be put close to solar collector on a plane which is inclined at the same angle as that of the solar collector. So in that case, you don't need to calculate IT. Remember the example where you calculated IT on an inclined surface, right? If you put your pyranometer at the same inclination, you don't need to calculate IT. It gives you the number IT directly. Okay. So this solar meter basically would be required to get the input energy, right? So whatever irradiance is measured in watt per meter square multiplied by the collector area in meter square would give you the rate at which the solar energy is falling on the collector. Now, these testing are many times done with artificial like radiation, solar radiation generators, because you want to produce or you want to keep it constant. If you test it outdoors, keeping the solar energy constant would be next to be impossible, right? Or you have to test it very close to solar noon in a clear sky. In that case, the variation would not be very high. So a solar meter is shown, which is for measuring the input energy. Then you can see here TI and TO are measured. And there is a flow meter, so you want to measure the mass flow rate. This flow meter may give you volume flow rate. You multiply it with the density, you get the mass flow rate, and TI and TO, right? So you measure inlet temperature of the fluid, outlet temperature of the fluid. And then a heater or cooler may be required, and a storage may be required, and there is a pump, and there is a flow control valve. So if you want to vary the mass flow rate, then you need this flow control valve, right? So the pump is pumping, let's say, at a constant rate, but you want it, let's say, 1 kg per second or 2 kg per second. So you can vary that by with the help of this bypass valve. So what you do is you don't allow all what is pumped by the pump to go this way. You may put it back into the tank. So what goes here is less than what is pumped by the pump. Okay, so these are the function of different things. So you want to test the collector at different mass flow rates, and you also want to test the collector at different inlet temperatures. Now, how can inlet temperature be varied? Inlet temperature can be varied with the help of this heater or cooler, right? So let's say you are testing a solar water heater, and at one point of time, you pump the water at, let's say, 40 degrees Celsius by, let's say, a particular flow rate, 40 degrees Celsius. Now you want to, let's say ambient is constant at 30 degrees Celsius. So you want to pump the water at 40 degrees inlet, 40-degree inlet temperature, right? Then next you want it at 50. So you may need a heater for that, and you pump it at 50, measure this outlet temperature, and make the required table. Again, you also want to test it at 60-degree inlet temperature. So with the help of this heater, you heat it to 60 degrees Celsius temperature. You have to maintain a particular temperature for all the tests, right? While you are maintaining this, let's say at 50, you might change the input heat flux, right? That IT might be changed. At one point of time, you make it IT equal to, let's say, 600 watt per meter square. Then in the next test, you take it at 700, then 800, 900, 1000. So those are the two parameters which are generally varied. You may vary TI and you vary IT. When you vary TI minus TA, right, that is delta T automatically is different, right? So these are the parameters which are varied, and then you what would you calculate at the end of for each test? You will calculate MCP delta T, that is useful energy, and you will also have value of IT. So IT into area would give you the input energy. So output upon input would give you the efficiency of the collector at a given condition. Okay. And then finally, you will plot this efficiency. Efficiency is output upon input. Output is MCP delta T. Input is IT into area. So you get the efficiency for each test, and then you plot efficiency versus delta T upon I. Okay. So that's shown here. Delta T upon, it's written GT. It is same as what we call IT. Okay. So this is on the horizontal axis for each test, Ti minus Ta upon IT, whatever values you have kept or set, that will be put here. And for that, how much is the efficiency? You will put a point for that. You will put a point for that. Then you change something. You change your delta T, and for the new test, again you put you measure the efficiency, that is input, that is output upon input. So you have another point, but you change your delta T, right? Let's say you have increased your delta T, so you will move on the right side. How do you increase delta T? Let's say Ta is same, Ti is increased. So earlier it was done at 50 degrees Celsius. You got a point somewhere here. Now it is done at 60 degrees Celsius. So you will get a point here. It means that higher the delta T, less the efficiency, right? Higher the delta T, less the efficiency. And you already know that this is going to be a linear chart, right? Because of the nature of the equation. Of course, this is for this is not considering the second order. Only this was expressed as a first order equation, which is more or less true if the temperature, operating temperature, or the delta T is not very high. So we'll keep ourselves limited to that case only. So this delta T, as it increases, the efficiency goes down. It means that if you operate your solar collector at high temperature, it is going to give you low efficiency, right? So you cannot compare the efficiency of the same collector, let's say, of the solar collector at 70 degrees Celsius operating condition and 50 degree operating condition. The efficiency at 70 degree is going to be lower. But how much lower? What exactly is the number? That will be available once the graph is plotted. So this graph is plotted while it is tested, right? Everybody doesn't have to draw this graph. You give that job to a testing agency, which can give you a certificate or which can provide you the performance of your solar collector. So they would do these tests and produce the graph for you. And once you have the graph, you can write the equation of this line, and that gives you that you can provide to your customer, right? If you are the manufacturer. Then so this delta T, as it increases, the efficiency would go down. And what about GT or IT? As the GT or IT goes up, you are actually moving on the left hand side, so efficiency will be higher. So higher the irradiance, higher the efficiency. So solar irradiance, if it is higher, it is always beneficial. It will not just increase the input energy, but it will also increase the efficiency of a solar collector. So this is a typical graph of a flat plate collector. As you can see, the slope is equal to minus FR, heat removal factor, into heat loss coefficient, and it is negative slope, right? It means that as delta T upon GT goes on increasing, the efficiency of the collector would go down. And the intercept is FR into tau alpha. Okay, N is written for normal because the collectors are generally tested at the normal irradiance. The radiation, solar radiation, is kept perpendicular, right? So this FR into tau into alpha is the intercept. So that if you operate your collector at the ambient conditions, right? Even then, the efficiency will not be, means Ti is equal to Ta, right? In collector, it is going to increase a bit. but Ti is equal to Ta. Right? In that case, even in that case, the efficiency will not be 100%. That is because there is optical loss, as well as the collector is operating at a temperature bit higher than the ambient conditions. Right. So this is the graph, the typical graph that you'll get for the flat plate collector efficiency, and it is plotted versus delta T upon GT. Okay, so I hope the concept about the efficiency, what are the parameters affecting the efficiency, how is the testing of a solar collector done to generate efficiency graph is clear, right? So once this graph is generated, you can get the equation for this graph, right? And you are going to get multiple points, and you are not going to get all the points on the same line, right? But you will draw a best fitting line with, if your test is good, then R square value would be high. And with such a good testing, you can fit a line through those points, and then you can give the equation of the line as the characteristic curve of your solar collector, which gives you the efficiency based on delta T upon GT. Okay, so that is about the efficiency. Now, just for little calculation and for better assimilation of the concepts, I have designed two examples which are actually very simple example. You just need to put values in the formula and you would be able to get the answer to that. So I'm just mentioning those. The total radiation falling on a plane of a flat plate collector is 900 watt per meter square. So this is your IT at a given point of time. The transmissivity of the glass and absorptivity of observer surface are 0.9 each. If expected overall heat loss coefficient is 3 watt per meter square Kelvin, okay, 3 watt per meter square Kelvin, then and entry temperature of the fluid and ambient 60 and 30, find the efficiency if the heat removal factor is 0.9. So actually everything is given. So you just need to use the formula. FR is 0.9, tau alpha 0.9, 0.9, this UL is 3, and TI is 60, and TA 30, and 900. So 0.64, 64% is the efficiency of the given collector you can expect. Right now, if you change something, then the performance might change. Like say in place of 60, if it is 70, then the efficiency you can expect that it will go down. If in place of 900, if it is 700, then you can expect that again efficiency would go down. Right? So you can, once you are given the parameters, you can calculate or you can estimate what would be the performance of my collector if something changes, right? If my operating temperature is this, then what will be the efficiency? That is what may be calculated. Okay. Again, one more example. The equation for efficiency of a solar collector is given by this 0.7133. So what is this 7133? It is actually FR into tau into alpha, and 3.544x. So what is this x? X is delta T upon IT, and the multiple to that is that is FR into UL is this 3.544. Ambient is at, let's say, at 35, and water temperature is 70, irradiance is 850. What is the expected? Actually, it's written 850, but perhaps in example, I have used it 800. What is expected efficiency of the collector? Transmissivity and absorptivity are 0.92 and 0.94. Right. So this, what is this x? X is equal to FR into Ti minus Ta upon IT. Right. So with this, you can get FR, which or equation for FR, and then tau alpha can also be calculated. Now FR into tau alpha is the intercept, that is 0.7133. So you can calculate FR now, which comes out to be 0.8248, and then you can put it in the formula for the efficiency of a collector, and you get the efficiency of the solar collector, right? So these are just two small examples given to so that you can have some calculations, and with the help of that you can assimilate the concept better. Right, so we are almost near the end of the discussion on a flat plate collector, uh, particularly the traditional flat plate collector. We may talk about the CPC, which is actually fixed collector but not flat plate collector, and evacuated tube collector will also be explained in the next class. Now, this FPC, flat plate collector, is a very popular design, particularly because of its simplicity and you need to keep it stationary, etc. And it is a well-developed technology also. If you want to keep the efficiency high or you want to increase it further, what measures might be taken? Of course, when you say what measures might be taken, it means that it may need some extra effort or in terms of research and development, or some you may incur some extra cost for this, right? So use glass cover with high transmissivity, so low absorptivity and reflectivity, or anti-reflective coating may be used. Low iron glass should be used so that the transmissivity is high. Absorber should have high absorptivity in solar spectrum and low emissivity in infrared spectrum. So for that you use a special material which is called selective coating, and with the help of that you can improve the efficiency of a solar collector. Then instead of single glass, you may use double glass, right? You know there was a single glass used, but then even that glass will reach a particular temperature which is higher than the ambient, and losses will start. Particularly when your operating temperature or absorber temperature is high, glass also will achieve very high temperature. So it might be beneficial, particularly when you are using somewhat higher temperatures, to put double glass cover rather than a single glass cover, right, to reduce the top loss. But of course, this increases the cost, this increases the may increase the maintenance, it may increase the weight of the collector. Using insulation with a very low thermal conductivity, right, so that also would help. And ensuring low temperature difference means having thin absorber plate, having high thermal conductivity for the absorber plate, and design of the tubes should be such that the heat transfer coefficient through the tube is high, and with the help of these things you might be able to keep your keep the temperature difference over the plate to be small, and in that case you will have somewhat lower losses from the absorber plate. So these are some of the measures which should be taken to improve or keep the efficiency of the flat plate collector high. So